So now we know we can place numbers on this Argand diagram. And what that does is it allows us to describe them in a different way, what we call mod-arg form. So the modulus of the complex number is the length of the vector, if you were to join it up to the origin. So there's our complex number, call it x plus iy. We could create a vector, join it up to 0, and the modulus would be the length of that vector. So I could drop down there, x, real part, y, imaginary part, and we get square root of x squared plus y squared. The symbol for modulus is the absolute value symbol, because again, that's all that absolute value is, distance from the origin. All right. But anyway, what it means now is, you remember the quick way of finding a reciprocal when I said it was the conjugate over z conjugate, which is, now I don't have to say the sum of two squares now. I can say, it's the conjugate over the modulus squared, because the modulus is the square root of x squared plus y squared. So there it is, the formal definition. And the argument is the angle it makes with the positive x-axis. These are also known as polar coordinates. So it's another way of defining a point on the number plane. And so to work that out, bit of trig, inverse tan of y on x would get that particular angle. Now when we're defining it, because of course angles you can keep going round and round and round, you have multiple answers for the same position. So we define it to be always between minus pi and pi. So we're never going to get a reflex angle. It's either positive or negative, acute or obtuse. Now when we get over to pi, because obviously pi and minus pi is the same position, then it's pi we use rather than minus pi. So 4 minus 4i. Okay, well the length of that vector, square root of 4 squared plus 4 squared, we get 4 root 2. The angle, now I write it this way, minus 4 on 4, because the position's really important. So I don't look at that and think negative 1. It is negative 1, of course, but when you put that into a calculator, tan will always give you back, for negative 1, it'll be a negative acute angle, won't it? Negative acute angle. Yes. But it is possible that the point could be in the second quadrant. Well, the calculator's not going to give you that. So that's why it's important you know the exact position. So you might even want to draw up a diagram. Now, for this one, I do want the negative acute angle. That's fine. But imagine it was negative 4 plus 4i. Still would come back with an answer of negative 1. Calculator's still going to give me that negative acute angle, but actually I want the obtuse angle. So you just got to be careful with that. So minus pi on 4. So every complex number then can be rewritten in terms of those two things. So yes, x plus iy if we're just using our regular Cartesian coordinates, but now x is r cos theta, and y would be r sine theta. Again, just a bit of trig would tell us that. So I could factorise the r out, we get r cos theta plus I sine theta, which is writing it in terms of its modulus and its argument. So the mod-arg form is that, r outside of cos theta plus I sine theta. You will see this shorthand notation of cis. Basically just stands for cos plus I sine. A lot of people use it. You just got to be careful that you don't confuse it with cos. So r is the modulus and theta is the argument. So 4 minus 4i, if I did put it in the cis notation, 4 root 2 cis minus pi on 4. Root 3 plus I. Well, modulus is 2. Argument, well this time they're both positive, so I'm looking for an acute angle. We're in the first quadrant. So pi on 6. 2 cis pi on 6. So if I wanted to go back the other way, so I had 6 cis pi on 6, well that's when it's useful to rewrite it as cos plus I sine, because now I'm just simply saying, what is the cosine of pi on 6? What is the sine of pi on 6? So I get 6 times root 3 on 2 plus a half I, 3 root 3 plus 3i. Some relationships which allow us to manipulate these numbers then. Okay, when it comes to modulus, if you want to find the modulus of z1, z2, certainly you could find the modulus of each individual one and multiply those together. That would work. So whether you do the multiplication first, then find the modulus, or find the two moduli, then do the multiplication, up to you. With an argument though, you've got to be careful. We don't multiply the arguments together, we actually add them. It's a bit like your log laws. When we're doing the log of two things multiplied together, we actually add logs. Multiplication by Z1 means we're going to rotate by the argument of Z2. If you think of the position, we're saying the argument is the angle, so we're adding on the angle of the other complex number, so it rotates the position, whatever the argument is. You can prove that quite easily. So let Z1 be R1 cis theta 1, Z2 R2 cis theta 2. So if I was to expand the whole thing out, Z1, Z2, ooh, there it is. Well, R1, R2, there's your modulus straight away, nice and easy. A pattern. Look at the real part. Cos minus sin. Whoa. Yes. And look at the imaginary part. Sin, cos sin. Ah. Whoa. Well, we recognise those. So we have the cos of theta 1 plus theta 2 plus I sin theta 1, theta 2. There's why we add the angles rather than multiply the angles together. Yep, yes indeed, we can prove that Z1, Z2, same as, and the arguments when we're adding. Now, of course, we could extend that through. If I have a whole heap, then I could just multiply all the individual moduli together to come up with the modulus of the whatever number that is, all those things multiplied together. And with the argument, I could just add everyone together to come up with a final one. Division, it's also true that you could do the division first, find the modulus, or find the different moduli, then do the division. With the argument, you would subtract, again, like the log laws. So from that, well, if I had to find Z1, Z2 over Z3, Z4, the modulus, I could find the modulus of each bit, and the ones on top I'll multiply together, the ones on bottom I'll multiply together, and then divide top by bottom. With the arguments, basically whatever's on the top of the fraction will be positive, whatever's on the bottom of the fraction will be negative. So it's, well, it's the argument of Z1 plus the argument of Z2 minus the argument of Z3 minus the argument of Z4. And if I wanted to raise it to the power of n, well, power of n just means z times 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 z. Shame we don't know what n is, isn't it? Z times z times z times z times z. Anyway, you get the idea. So by what we've just seen is we could get each individual one and go, the answer, that's easy. That's mod z times 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 mod z mod z times mod z times mod z times, and we'd end up with mod z to the power of n. Whereas with the arguments, I'd be going argz plus argz plus argz plus argz plus argz plus argz plus argz, and so we'd end up with n lots of the argument of z. So here's this wonderful expression. Yep, I could multiply the two together, do the division, come up with an answer. An alternative, well, I could just find the modulus, and the modulus would be each individual moduli. So square root of 5 squared plus 1 squared times square root of 2 squared plus 1 squared divided by square root of 3 squared plus 2 squared. Oh, look at that, 1326. That was nice, wasn't it? Weird how that works out. We get the square root of 10. The arguments? Oh, unfortunately, they're not all exact values. Inverse tan of 1/5, inverse tan of minus 1 on minus 2. That's just reminding me about the quadrants. But then on the bottom, I'd get minus the inverse tan of 2/3. So I'm going back to degrees now and getting approximations. 11 degrees, 19 plus. Well, that would be in the third quadrant. So I get a negative obtuse angle. So minus 153.26. But then I'm subtracting the acute angle of 33.41. I end up with minus 175.48. So I could work out my number from that. It's going to be an approximation, of course, because of the argument not being an exact value. But it does provide us with an alternative. Okay. Well, what if I want to shift the reference point? Remember, we've seen this whole thing with graphing. We can sometimes move it from the origin to somewhere else. So here's a typical sort of one. Yeah, we've got a circle. We've moved the centre has moved to 1, 2. Same idea in the Argand diagram. Okay. There's z, and mod z means the distance from z to the origin. Argument of z, the angle that position vector makes with the x-axis. Well, what about if my reference point's not the origin? It's over here at some other complex number, w, a plus ib. Well, I can still join those two. If I think of it as a vector, the length of head minus tail So it would be the magnitude of z minus w. The arguments would still be the angle it makes with the horizontal. So what I've called alpha there, whatever that horizontal is, that angle in there would be the arguments of that particular vector. One-dimensional, very boring. Okay.